This is question 7 from set C of John Short's textbook. You can see I've already prepared a diagram. What we have is a hot air balloon that is tethered, and we have an observer that notes that the hot air balloon is due west of the observer. The way I've set it up is so that the hot air balloon comes out of the origin, and the observer will note then that the hot air balloon is west of them if you place the observer due east of the hot air balloon. That's observation point 1. We are told the angle of elevation to the hot air balloon is 44 degrees 18 minutes. We are then told that the observer travels due south for 5 kilometres. When we're going due south, we have to make sure that we follow the north-south axis that we've drawn in obliquely in the original diagram. So we follow that line down for 5 kilometres, and finally you're told that from the second observation point back to the hot air balloon, the bearing is north 13 degrees towards the west. Another important thing when we're taking bearings, always imagine that you're going to the base of the hot air balloon. Don't start considering the hot air balloon up here. On this side of the board, I have redrawn 2 triangles that we've taken from our original 3-dimensional problem. If you look at the first triangle up here and come back over, you'll notice that I've put the triangle from observation 1 up to the hot air balloon, back down to the tether. The second triangle I've drawn is from observation 1 to observation 2, back up to the tether point. If we call the tether point O, and we come over here, our triangles would be labelled in the following way. O, we'll call that B for balloon, we'll call this observation 1. This is going to be observation 1, observation 2, and back to the O for the tether point. Now, if you look at these 2 triangles, it's possible to use this triangle here to get the distance from observation 1 back to the tether point. That's a common line with this one on our first triangle. So we're going to find this distance here. To do that, we're going to use tan. We have a right angle triangle because this line is running east-west and that's running north-south. Tan theta equals opposite over adjacent. Therefore, tan of 13 degrees equals to the opposite. We can call that x1 if we want, over the adjacent. Now, if we enter that into our calculator, we'll get an x1 value of 1.15 kilometres. Once we've got that value, we can place it back into this triangle here. Now, if you look at this, this is a right angle triangle. We have an angle, we have a line, we can find this distance here. We'll call this distance x. That means that we're trying to find the opposite, and we know the adjacent. Again, we're going to use tan theta from our right angle trigonometry. So tan 44 degrees 18 minutes is going to equal to the opposite divided by the adjacent. If we place that into our calculator, we should find that x equals to 1.13 kilometres. If we come back to the diagram that we drew at the beginning, you can see that we've found this value here, which is 1.15 kilometres, and ultimately we've been able to find the height of the hot air balloon, which is 1.13 kilometres. That's all it is.